Good morning, good afternoon, and good evening, everyone. So today I'm going to be doing something a little different. I'm actually going to start a new series, and we're going to go over this book called An Intro to Statistical Learning with Applications in Python. So now I'm trying to get into something with machine learning and data science here. Um, so yeah, let's just hop right into it. So here, really, I'm just gonna go through the entire book in this series. Um, so yeah, okay, it was printed at this time. Statistical learning refers to a set of tools for making sense of complex datasets. In recent years, we have seen a staggering increase in the scale and scope of data collection across virtually all areas of science and industry. As a result, stat learning has become a critical toolkit for anyone who wishes to understand data. Uh, okay, first books, applications in R. However, in recent years, Python has become increasingly popular. That's also why I picked the Python version, because there's actually an R version of this one. Um, and yeah, an intro to stat learning with Python applications. Um, okay, so I'm just skimming through that because that's just an intro. Some of the topics we'll be talking about, and I'm gonna admit I haven't seen these before. We're gonna talk about stat learning. We're gonna talk about linear regression. We're gonna talk about classification, resampling methods, linear model selection and regularization, moving beyond linearity, tree-based models or methods, support vector machines, deep learning, survival analysis, unsupervised learning, multiple testing. And yeah, okay, let's start with the intro. So, what is statistical learning? It's a set of tools for understanding data. And these tools can be classified into things supervised or unsupervised. Broadly speaking, supervised involves building a statistical model for predicting or estimating an output between or based on one or more inputs. Problems of this nature occur in fields as diverse as business, medicine, astrophysics, public policy, and here with unsupervised, there are inputs but no supervising output. So here we can learn relationships and structure from such data. And to provide an illustration, we briefly discuss three world data sets that are considered in this book. So first is wage data. Uh, So we have a wage data set throughout this book, and we examine a number of factors that relate to wages for a group of men from the Atlantic region of the United States. In particular, we wish to understand the association between an employee's age and education. Okay, so what's the relationship between the employee's age as well as their education, their year, and their wage? So there has to be some correlation between these four variables. Consider, for example, the left panel of figure 1.1. Can I like go there? Oh, I can. Oh, that's nice. Which displays wage versus age for each of the individuals in the data set. Okay, wage versus age. Okay, so we're talking about this one here, the first graph. So my wage is if I'm using mathematical terms, it's the vertical axis, and my age is my horizontal axis. And it seems to me this is some sort of scatter plot or a set of points, and there's this weird blue line there or blue curve. Um, okay. So there's this evidence that wage increases with age, but then decreases again after approximately age 60. So the idea is as the people age, right, as the age increases, as people get older, their wage increases. But then as it reaches 60, it starts to kind of go down, their wage, right? Uh, okay. The blue line, which provides an estimate of the average wage for a given age, makes this trend clear. So that's how we indicated it, which is this blue line. So here it kind of goes up 20, 40, all the way to 60, and then from 60 it starts to go down. Uh, so that's what makes this trend clear. And given an employee's age, we can use this curve to predict his wage, right? However, it is also clear from this figure that there is a significant amount of variability associated with this average value. That's true. And so age alone is unlikely to provide an accurate prediction of a particular man's wage. So we can't just predict a person's wage based solely on age. We can't predict wage based solely on age. Oh, that's a rhyme. And so here's just a description of what this data is. It contains income survey info for men, so specifically for men, from the Central Atlantic region of the United States. Uh, yeah, so the first graph is wage as a function of age. And on average, wage increases with age until about 60 years, at which point it begins to decline. The center graph is wage as a function of year. Here we see there is a slow but steady increase of approximately $10,000 in the average wage between 2003 and 2009. Yes. So as my years increase, or as the years go by, my wage is slightly increasing. So I don't know how they were able to do that. But here we can see from this blue curve. Okay, what else? Uh, yeah, right. In my right now, we have a box plot, and this box plot displays wage as a function of education, right? So given the education level, it will give us a corresponding wage. One being the lowest level. So the education level one means no high school diploma, and five having an advanced graduate degree. And so the higher the education level, the higher the wage. We also have information regarding each employee's education level and the year in which the wage was earned. So the center and right-hand panels of figure 1.1, which displays wage as a function of both year and education, indicate that both of these factors are associated with wage, right? So we have two things that help us determine what the wage of a person might be, not only its age, but also its year and education. Okay, wages increase by approximately 10K in a roughly linear or straight line fashion. So it's talking about this graph. It's roughly linear, right? Between 2003 and 2009, though this rise is very slight relative to the variability in the data, wages are also typically greater for individuals with higher education levels. So men with the lowest education level tend to have substantially lower wages than those with the highest education level. Clearly, the most accurate prediction of a man's wage will be obtained by combining his age, his education, and the year. So the most accurate prediction would be to combine all of these variables together, age, education, and year, to give a more accurate prediction of that person or that man's wage. And so in chapter 3, we discuss linear regression, which can be used to predict wage from this data set. Ideally, we should predict wage in a way that accounts for the nonlinear relationship between wage and age. In chapter 7, we discuss a class of approaches for addressing this problem. So yeah, there's also something a bit iffy. There's this ick about predicting wage. Because honestly, there's a lot of variability in the data. How were they able to find this blue line, right? How are they able to find these curves? Okay, so I'm actually gonna do a little note here. Let me just set up my notebook. I'm gonna take notes while I do this so that I don't forget my. I'm just gonna address the key points that we've discussed so far. Uh, let me make let me make a new notebook. I should have done this before recording this video, but anyways. Uh, okay. Let me quickly make a new notebook. Uh, not notebook. We're gonna call it Intro to Stat I should have it here. We're gonna call this introduction. And here we're gonna call this, what do I call this? Okay, I don't know how to organize this thing yet. Um, yeah, we can just call it whatever. We can call it introduction, I think. Yeah, I'm just gonna call it intro. So maybe introduction with three dataset examples. Okay, and let me, okay, I should have done this before. I'm gonna go to my notebook. I'm actually gonna open this thing. Um, okay, I'm gonna stop sharing real quick. And I'm gonna go here. Okay. This is just so that I can make notes. So far what we talked about was, well, basically, what is statistical learning? Should have done this before. So here's what I'm gonna do. While I'm making this video, I'm gonna read through the book and I'm gonna make some notes just to summarize what I've talked about so far. Here we talked about two ideas. We talked about supervised and unsupervised. Okay, why is it like that? My notes are acting funny. Unsupervised, right? Those are the two things we talked about. And we mentioned that, well, supervised involves building a model for predicting. So the use of this is for predicting. It's also used for um, estimating. And, but yeah, an output based on inputs with an S. So kind of like if you talk about it in a math sense, it's kind of like a function if you think about it. We have our function y. I mean, we have an output y. We plug some value x into our function, or we could have like our output z, and we plug in two inputs, or we could have some completely something different. We could have b, and we have three inputs. That could be a mathematical way of describing that. Okay, anyways, before I digress, it's unsupervised. Uh, these are inputs, but no supervising output. So here we have no supervising output. Now, this is something I cannot describe yet. I don't know what this exactly means. But the benefit of having no supervising output is we can learn relationships and structure from the data. So more like learn new things about data. Something like that. And then we talked about wage data, right? And here in the wage data, we're given three graphs, right? So let me just copy and paste the three graphs. Here's what I like to do. When I go through a book or some sort of literature, or even like, yeah, because this is a, let's be honest, this is a technical textbook. When I go through this, I'm just gonna make something out of it. So here we talked about how a certain age tells us something about its wage, right? So we could say, let me just write it in my own words. If we plug an age in our function, we get a corresponding wage, right? And so this means that as my age increases, I get a certain wage. And then once my age reaches 60, it decreases. And similarly, we can do it for a year, which will also give us a wage. And we can also do it for education level, which will also give us a wage. But then we talked about this being not the most accurate prediction if we only use one of them, right? So it's not super accurate. Uh, by itself. So what do we need to do? Well, most accurate would be to use all of them. So if we plug in some function, some year, and some education level, and we get the wage, right? So the idea is we have to include all of them, find the most accurate wage of that person, right? So that's really all we talked about. Okay, so let's can I switch to the screen I'm sharing? I hope I can do that. Oh, wow, I can do that. Or am I doing it? Am I in that screen? Okay, I'm in that screen. Next, we talk about stock market data. So stock market data, the wage data involves predicting a continuous or quantitative output value. This is often referred to as a regression problem, right? Okay, so I'm not a statistics person, so I'm actually good. I know what continuous means, right? Continuous means in mathematics, well, there are no holes, no gaps, or none of that, right? So here we can see in our lines that this is continuous because there's no holes, there's no gaps. This one's also continuous because there's no holes and gaps. This one I can't really tell, but I'm assuming you can make a blue line out of that, just predicting how education level increases, then my wage also increases. So there's a linear relationship with those two, or at least in the beginning, right? Because not everything is linear, as they say. Um, yeah, this is often referred to as a regression problem. So maybe we can Google a bit. What is regression in statistics? So it's a set of techniques used to model and analyze the relationship between a dependent variable and one or more independent variables. So we're finding a relationship between my independent variables as well as my dependent variables. So I'm actually gonna quickly write that out just so that I know what I'm talking about. Here we move to stock market data. Stock market data. And here we talked about regression. And regression definition. It's the basically it's the set of techniques used to determine a relationship. So I don't know what these techniques are yet. Um, Between independent and dependent variables. So it's that idea. And then we also talked about, or actually, that's fine. I was gonna say what is a stock market, but I'm gonna assume that you guys know it. I mean, yeah, they're probably gonna tell us what it is, anyways. Okay, let me share that back again. Where was I? Here. So, okay. However, in certain cases, we may instead wish to predict a non-numerical value. So that is a categorical or qualitative output. And oh, so we did find something new, right? So let me let me go back uh and do my so here's the thing. We have two things or two types of data that we've just discovered. We have this idea of categorical or qualitative data. And this basically means uh, data with no numbers, right? And then we have quantitative data. And it's the other way around, data with numbers, right? So here we're just unlocking definitions as we go along the way. Um, yeah. Okay, let me share this thing again. So for example, now we proceed to an example. In chapter 4, we examine a stock market dataset that contains the daily movements in the Standard and Poor's 500 stock index over a 5-year period between 2001 and 2005. Let's actually Google it just to be super, super sure. What is a stock market? What is that? So it's an equity market, a marketplace where investors buy and sell shares or stocks of publicly traded companies. It's a system where individuals and institutions can invest in businesses and potentially profit from their growth. So essentially, it's a platform for companies to raise capital and for investors to participate in the ownership and potential gains of those companies. So it's kind of like we have different kinds of companies. Each companies have a certain number of stocks, and these each of these stocks have a certain cost or price, and we have investors, and basically they buy and sell shares or stocks. Stocks and shares are the same. And when they do that, if they buy stocks, then that will represent their ownership of the company that they bought their stocks from, right? So that's what that is. Okay, I'm not gonna dive too deep into that. Okay, so we examine a stock market dataset that contains the daily movements in the Standard and Poor's 500 stock index over a 5-year period. So here we're looking at a specific stock, the movement of that stock over a 5-year period from 2001 to 5, and we refer to this as the S market data. And the goal is to predict whether the index will increase or decrease on a given day. So here we're trying to predict. And using the past 5 days percentage changes in the index, here the statistical learning problem does not involve predicting a numerical value. So here we're predicting a qualitative or categorical value. or output. Instead, it involves predicting whether a given day's stock market will fall into the up bucket or the down bucket. Okay, I don't know what that is. This is known as a classification problem. And that makes sense, right? Because we're classifying whether it's going to be up or it's going to be down. The model that could accurately predict the direction in which the market will move would be very useful. Okay, let's look at that. So the left-hand panel of figure 1.2, so this one, what does it say? Or what is it? We have two box plots, 1 and 2, okay, of the previous day's percentage changes in the stock index, right? Mhm. Let me just try to wrap that around my head. Uh, One for the 648 days for which the market increased on the subsequent day, and one for the 602 days for which the market decreased. So, okay, the first one is for the 648 days for which the market increased. Uh, Percentage change. Okay, on the subsequent day, and one for the 602 days for which the market decreased. I'm assuming okay, of the previous day's percentage changes in the stock index. 648 days for which the market increased. Uh, for which the market decreased. Yeah, the two plots look almost identical. Yeah, they almost look the same if you think about it. So here the percentage changes like what? If I can still read the box plot. So here are the data points, these points. Here's the box plot. And then this black line in the middle, inside the blue and the orange box, is what we call, if I'm remembering my stats, probably the average, right? So the percent change here is like what, 0 point something percent? And then this one's a bit lower. Or actually, this might be zero. I'm not super sure. It's hard to read this though. Oh, actually, I should have read this one first. Left box plot of previous day's percentage in the S&P index. Oh, the percent change for the days which the market increased or decreased obtained from the S market data. Uh, okay. Yeah, it looks almost the same. Suggesting that there is no simple strategy for using yesterday's movement in the S&P to predict today's returns. The remaining panels, which display box plots for the percentage, changes 2 and 3 days previous to today. 2 and 3 days previous to. Oh, so this is the next day. And then this is the next day. So this is the second 2 days previous, 3 days previous. Oh no, my bad. Not next day. This was yesterday. This was 2 days ago. This was 3 days ago. I'm going in the future. It's going to the past. Uh, Here, what do we see? Okay, I'm gonna admit I cannot interpret a box plot. So I'm gonna have to look that one up. But here we can see like the data points here on top of this blue box plot. It's kind of gone here in the 4 to 6. And then here down, there's a lot more than what previously used to be. But really, they're black. The black lines are mostly the same. And this one I think is both zero. Anyway, I'll leave it to text to interpret this. Um, yeah, the remaining panels for which display box plots for the percentage change 2 and 3 days previous to the day similarly indicate little association between past and present returns. So Really, yeah, there is a lack of pattern because we cannot see what's the difference between any of those. In the presence of strong correlations between successive days' returns, one could adopt a simple trading strategy to generate profits from the market. Nevertheless, in Chapter 4, we explore these data using several different statistical methods. Interestingly, there are hints of some weak trends in the data that suggest that, at least for this 5 year period, it is possible to correctly predict the direction of movement in the market approximately 60% of the time. Uh, don't know where they got that value 60%. Because basically, what this is saying here is it's hard to find a pattern since they are pretty much the same, right? Do I need to take note of that? Sure, I can take note of it for a bit. Maybe I'll also add something about box plots. This is honestly just for myself because I can't read box plots. Uh, okay, so let me just put in the graph here. And here, basically, the summary uh, of what this is saying is that it's hard to find a pattern. Therefore, I realized I'm not sharing my screen. Okay, let me share. So I've taken a screenshot of this plot and then I'm writing. So basically what the idea is here is it's hard to find a pattern because of the percentage changes between yesterday, not between, from yesterday and 2 days and 3 days ago's data. It's very little. It's so minor. It's impossible to, well, what was the goal of this problem again? To predict, I think. To predict whether the index will increase or decrease. Therefore, it's hard to predict. Uh, Future data. So that's basically the summary of it all. Um, but yeah, I hope that makes sense. And I don't know where they got that 60%. That one's just interesting. I don't know where they got that one. Anyways, can I? It's good that you can like highlight this thing. Oh, wait a minute. Oh, the 60% of the time refers to a new figure. Okay, cool. Okay, now we look at gene expression data. So I'm also gonna write that out in case we can make some notes on something. So gene expression data, the previous two applications illustrate datasets with both input and output variables, right? We take an input, we got corresponding output, kind of like a function. However, another important class of problems involves situations in which we only observe input variables with no corresponding output. So for example, in a marketing setting, we might have demographic information for a number of current or potential customers. We may wish to understand which types of customers are similar to each other by grouping individuals according to their observed characteristics, right? Uh, so here we're now going through a case in which we have input variables, but we don't have a corresponding output. What does this sound like? Sounds like unsupervised statistical learning, right? Because we're given input. If we take a look again at my notes, I'm just going to read that. We have no supervising output, so we learn new relationships or basically new things about the data. So for example, in a market setting, we might have demographic info, so name, age, year they were born, stuff like that, where they live, for a number of current or potential customers. We may wish to understand which types of customers are similar to each other by grouping individuals according to their observed characteristics. So we're grouping them based on certain uh, or particular characteristics, most likely from their demographic info. This is known as a clustering problem, right? So let me just uh, note that real quick. So now we're looking at the idea where we have a clustering problem. And what clustering means is we're grouping data based on certain descriptions or characteristics. We're clustering them. Okay, let me go back. Where was I? Unlike in the previous examples, here we are not trying to predict an output variable. We devote chapter 12 to a discussion of statistical learning methods for problems in which no natural output variable is available. Yeah, so here we have some problems where we're not necessarily trying to predict a certain output based on some input. So it's different from functions. And here we consider the NCI 60 dataset. And I'm assuming it's this one, right? I'm not sure. Oh no, this was the S market data. Okay, let's look at this one real quick, actually. How did they get the 60%? So here we fit a quadratic discriminant analysis model. What? To the subset. So when we say subset, we're just looking at part of the S market data. We're not looking at its entirety, corresponding to the 2001 to 4 time period. What was I think it was 5, right? Okay, I'm gonna be honest, I forgot. What's the Oh yeah, from 1 to 5, 2001 to 2005. This one's only from 2001 to 4. So that's the subset. And predicted the probability of a stock market decrease using the 2005 data. On average, the predicted probability of decrease is higher for the days in which the market does decrease. Based on these results, we are able to correctly predict the direction of the movement in the market 60% of the time. Where is that? Let me just Google that real quick. What in the world is a quadratic discriminant analysis? So here I'm just really trying to go through each of them, Googling my way. It's a classification technique, so classifying data that assumes each class has a unique covariance matrix. So something about linear algebra, or I'm not really sure. There's something in scikit-learn, which is a module in Python. Mean and covariance. Cool. Kidding. Linear boundaries. Okay, maybe a simple definition. Let's see. Classifying data points into different groups or classes based on their features. Okay. Allows for nonlinear decision boundaries between classes unlike its linear counterpart. What does that mean? What's discriminant analysis? It aims to find a set of functions that best separate different groups of data points. These functions are used to classify new, unseen data points into the most appropriate group. And then linear is the data from each class has the same covariance matrix, meaning the same shape and orientation of data spread. And QDA, or quadratic discriminant analysis, relaxes this assumption, allowing for different covariance matrices for each class. Curved nonlinear decision boundaries. Okay. Okay. So something to look at more deeply. But not now. I'm just going through an intro. Uh okay. What am I looking at now? Oh yeah, here. So again, going back from the stock market data, this gene expression data, you consider this data set NCI 60, which consists of 6,830 gene expression measurements for each of 64 cancer cell lines. Uh, Instead of predicting a particular output variable, we are interested in determining whether there are groups or clusters, right? So clustering data among the cell lines based on their gene expression measurements. So that's something biologists would know. I'm not a biologist. I'm only a math guy. Anyway, this is a difficult question to address in part because there are thousands of gene expression measurements per cell line, making it hard to visualize the data. I didn't know that. The left-hand panel of figure 1.4 addresses this problem. I'm assuming it's... Oh, there you are. Okay. Hmm. By representing each of the 64 cell lines using just two numbers. Oh, now we go into math. Z1 and Z2. Z sub 1 and Z sub 2. These are the first two principal components of data, which summarizes the 6,830 expression measurements for each cell line down to two numbers or dimensions. While it is likely that this dimension reduction has resulted in some loss of info, uh, it is now possible to visually examine the data for evidence of clustering. Cool. Deciding on the number of clusters is often a difficult problem, but the left-hand panel of figure 1.4 suggests at least four groups of cell lines, which we have represented using separate colors. Oh, now we're describing this thing. Wait, let me go back. Okay, let me just summarize what we talked about. So instead of predicting a particular output, right, based on some inputs, uh, we are interested in determining the clusters or groups among the cell lines based on their gene expression. Okay, you know what? I'm gonna Google my way through. What's a gene expression? Is that like I forgot my biology. Is that like the uh, adenine, guanine, cytosine? Or I'm talking about something different? Information from a gene is used to synthesize a functional gene product, most commonly a protein, encoded in DNA, resulting in the production of RNA. Oh my goodness, this is not my thing. Maybe a simple definition. I just wanted a brief definition of what this is. Okay, it's how a cell turns on a gene to make ribonucleic acid. Don't ask how I know that. And then proteins, which are the building blocks and workhorses of a cell. So it's like uh we okay, I can't explain this. It's how a cell turns on a gene to make RNA. What was that? Using info in a gene to create a protein inside a cell. Okay, so it's a gene. We use the information in that gene to create a protein inside a cell. Okay, so it's the process of creating protein. That's it. So we'll just leave it at that. Uh, okay. And here we're saying that it's a difficult question to address because there are thousands of gene expression measurements. So we have thousands of info, thousands of data on the gene per cell line. So we're just saying so not even the gene, but we have thousands of data that we have to look at, which makes it hard to visualize this data. And so we address this problem by representing each of the 64 cell lines. Don't know where they got that 64 cell lines. We use them. We use two numbers to represent these lines, these cell lines. Um, okay. And if we reduce them to two numbers, we might lose information of the gene, right? But it's possible to visually examine the data for evidence of clustering. And deciding on the number of clusters is often a difficult problem. That's true. But the left-hand panel of figure 1.4 suggests at least four groups, which we have represented using separate colors. And in this particular dataset, it turns out that the cell lines correspond to 14 different types of cancer. Ooh. However, this info was not used to create the left-hand panel. The right-hand panel of 1.4 is identical to the left-hand panel, except that 14 cancer types are shown using distinct colored symbols. Let's actually look at what I'm saying. Uh, okay, we represented them with Z1, Z2 in 2D space, right? This is 2D. Uh, oh, here we clustered them, right? So these are the blue data, the red data, I don't know what that is, I'm colorblind. Like another shade of blue data, and then a green data. Then here we put shapes. I don't know, we have more data here, I think. Oh, actually, we don't. We don't have more data here. We're using the same data, but then we have different shapes as well as different colors this time. So that's interesting. Oh, so the right-hand panel shows the 14 cancer types. And there's clear evidence that cell lines with the same cancer type tend to be located near each other in this 2D representation. In addition, even though the cancer info was not used to produce the left-hand panel, the clustering obtained does bear some resemblance to some of the actual cancer types observed in the right-hand panel. This is really interesting, though. Yeah, this provides some independent verification of the accuracy of our clustering analysis. Right. So just to summarize, basically, this is a representation of the gene expression data in 2D space, Z1, Z2. Each point corresponds to one of the 64 cell lines. Then there appear to be four groups of cell lines, which we have represented using different colors. And in the right-hand side, right hand panel, it's actually the same as the left-hand panel, but we represent each of the 14 different types of cancer using a different colored symbol. Cell lines corresponding to the same cancer type tend to be nearby in the two-dimensional space. So here, surprisingly, we just use information on the gene, um, but then we were able to do some clustering analysis to determine uh, 14 different cancer types. So that's something that clustering analysis can do with the data. That's really interesting, though. Okay, so let me summarize that. I'm gonna Yeah, so when I learn something, I like to repeat it in my own words. So here we talked about clustering. What else do we talk about? I'm not gonna explain the gene thing anymore. Basically, uh, so here sometimes instead of predicting a particular output, like the one we did before, we were predicting particular outputs. That's why we made that line. So instead of doing that, well, we want to cluster or group data. So sometimes we do that. And here in this data set of gene expressions, we definitely did that. So yeah, instead of predicting a particular output, we judged them based on the we judged. We uh we grouped them, or we did a clustering analysis of the data, and we were able to gather some insights, such as determining, oh, there were 14 cancer types, right? But yeah, okay, I'm not gonna go into the in-depth thing, but the idea of clustering um, analysis. So let me just take a screenshot of that. Even the figure description has everything that we basically want to say about the data. So not always do we have to find a particular output, but sometimes it's also good to cluster them based on certain characteristics or based on the information of the gene in this case, in the biological context. And then that's where we that's where we're able to let me just highlight it actually. 14 different types of cancer. Yeah, that's where we were able to do it because of a clustering analysis. Okay, so hmm, let me go back to the screen I'm sharing before I end. So now we actually introduce statistical learning. Finally, huh? So this term is fairly new, and many of the concepts underlying the field was developed or were developed long ago. At the beginning of 19th century, the method of least squares was developed, implementing the earliest form of what is now known as linear regression. So what is linear regression? This approach was first successfully applied to problems in astronomy. Linear regression is used for predicting quantitative values such as an individual's salary, in order to predict qualitative values, so categorical values, such as whether a patient survives or dies, or whether the stock market increases or decreases. Linear discriminant analysis was proposed in 1936. In the 1940s, various authors put forth an alternative approach, logistic regression. So now these are some statistical techniques which I have yet to learn. And we're going to go through these techniques in this series. In the early 1970s, the term generalized linear model was developed to describe an entire class of stat learning models that include both linear and logistic regression as special cases. And by the end of 1970s, many more techniques for learning from data were available. However, they were almost exclusively linear methods because fitting nonlinear relationships were computationally difficult at that time. That's true. I can see it. In my case, like it's hard to fit the data if we don't have a pattern. Having a linear pattern is pretty much easy, right? So, okay, by the 1980s, computing technology improved sufficiently that nonlinear methods were no longer computationally prohibitive. So we were able to develop, apparently, as the text says, we were able to develop nonlinear methods um, of computing these. And in the mid 1980s, classification and regression trees were developed, followed shortly by generalized additive models. Neural networks gained popularity in 1980s. Support vector machines arose in 1990s. And since then, stat learning has emerged as a new subfield in statistics, and it focuses on supervised and unsupervised modeling and prediction. In recent years, progress in stat learning has been marked by the increased availability of okay, so it's the Python, uh, okay, to transform the field, yada, yada, yada. And so we have a book, there's a history, which is, okay, so there's the elements of statistical learning, which I actually plan to read sometime soon, just not now, because I don't have any stats knowledge, to be honest. It's like minimum to none. It's ephemeral. Okay. Um, and yeah, what else? Recent years, stat learning. So basically, it's a more accessible version of ESL, right? Because it's less technical. So actually, the series is going to be more of intuition, more of just exploring stat learning in a non-technical way, or not really non, in a less technical manner. And in teaching, what's this? Yeah, okay, so it's relevant, stuff like that. I can see why statistical learning methods are relevant. Can be applied, yeah. Um, yes. Okay. And it's also written in program in Python. Okay, so I mean anyone who's interested in reading this book, um, scientists, engineers, data analysts, scientists, quants, also less technical individuals with degrees in social sciences or business. Okay, so there's this expectation that the reader will have had at least one elementary course in stats. I've taken one in high school, I guess, like measures of central tendency and stuff like that. Uh, standard dev and variance. I've taken some of that. Um, but yeah, I mean, if I haven't seen something in this book, definitely I'll be sure to like make a supplementary lesson on it. It's really also for myself, but it's also for others who, or for the ones who are watching right now who don't have sufficient stats background. Okay. Yeah, they review linear regression. Okay, mathematical level of this book is modest. There is some uh, introduction to matrices, which I did talk about in my scientific computing series, which you guys can check out. Intro to Python. The first edition apparently was used to teach masters and PhD. Okay. Uh, and advanced undergrads who have already taken a course on linear regression. Uh, okay. So this is basically a supplementary text, but I might just go through it like just for fun, to be honest, because I'm also trying to explore machine learning and data science in a much mathematical or code-like way. It doesn't matter, but I'm interested. Uh, okay, we have notation. Uh, yeah, we go through some notation here. Organization of this book. Okay, let's go through the notation actually. So choosing the notation is a difficult task. So they adopted some notational conventions as ESL. Okay, so they use N to represent the number of distinct data points or observations in their sample. P is the number of variables that are available for use in making predictions. So for instance, the wage data contains or consists of 11 variables for 3,000 people. So we have N equals 3,000 and P equals 11 variables. Note that throughout this book, we indicate variable names used color font. So yeah, they put color font on the variable name. So here in this case, wage, year, age, race are variable names. And in some examples, P might be quite large, such as on the order of thousands or even millions. This situation arises quite often. Okay. Uh, okay, we have some um, matrix stuff. I might actually just go through this. Okay, let me use my notes. Uh, let's go through this using my notes. So let's go through some notation. Notation to just so that we get the notation out of the way. So here we say n is the number of distinct data points. So let's say number of distinct data points slash observations. And we say P is the number of variables available for use in making predictions. So we're just going to say number of variables used for predictions. What else? Okay, let's go through some matrix algebra notation. So here we say we let xij represent the value of the jth variable for the ith observation. So let's just go through it. So we say xij, this is the value of jth variable for ith observation. So we did talk about this in scientific computing, where we referred to I as my row and my j as my column, right? And here we're saying the rows are the observations. So the rows are my observations, and the j is my variable or my columns, right? Okay. And here, let's do a little bit of math. We're saying I starts from 1 to all the way to n, because these are the number of observations. And then what else do we know? And P is from 1 to all the way to, well, P. Oh, no, not P. I meant J. My bad. J. Right? And then what else do we know? Okay, so throughout this book, I will be used to index the samples or observations from 1 to n, and J will be used to index the variables from 1 to p. Okay, so here we let X denote an n by p matrix. So we're going to say X, capital X, is an n by p matrix. Let me just... So here, I'm going to use this notation. It's in my scientific computing course, where I talked about vectors and matrices. I'm just saying that that X, my matrix X, is an n by p matrix with elements, or with xij elements. So here, if I'm just going to write that out, well, I have this matrix X. And I go from x1, x11, x12. Right, so this is my my row. I'm in my row 1. And then my j is my column, or my, in this case, in the statistical context, my observations. No, my columns are, my bad. My columns are my variables, and my rows are my observations. And I go all the way to x1. I'm assuming this is p, right? Yeah. Then we have x21. I'm assuming this is xn1. And here I have my xn2. And I keep going to xnp. Yeah, this just goes all the way. All right. So for readers who are unfamiliar with matrices, it is useful to visualize X as a spreadsheet of numbers with n rows and p columns. Right. So that's the idea, just like I previously mentioned. N is the number of rows, p is columns. At times, we will be interested in the rows of X, right? Which we write as x1, x2, all the way to xn. Here, xi is a vector of length p, containing the p variable measurements for the ith observation. So we're gonna say at times we're interested in particular rows, right? I'm not sure when, but we're gonna be interested in some of them. In rows of X, right? So here we're gonna say X sub I is a vector length. So a vector is just a matrix that only has one column. A vector is a matrix that only has one column. And I did do a deep dive on matrix in my calculus and scientific computing course, so you guys can check that out. I think you guys should check out the scientific computing one because that one's more applicable to this case. So it's a vector length of p, right? So we say our notation would be like this: xi goes from xi1, which indicates uh my first one, xi2, all the way xip. I is some row, right? I is some row that we have, and here p is the length, something like this, right? Okay, so vectors are by default. Let me actually double check if my notation's right. I feel like I'm messing something up. All of these go from 1 to n. This one's an I, which is kind of weird. Okay, let's just say, just to complete this notation, I goes from 1 to n, just to be super, super sure. Oops, my bad. Why did I do that? Yeah, and then my p is just, yeah, my j goes from 1 to p. Okay, yeah. I just want to be satisfied with the notation. So that's a vector, right? And for example, if we use our wage data, we say that x sub I is a vector of length 11, right? Because that's the number of uh, observations that we have. And it consists of year, age, race, and other values for the ith individual. At other times, we will be interested in the columns of x, right? Let's actually do an example. Yeah, just to contextualize. I like contextualizing these things. So in the wage data that we discussed, we say that x sub I is a vector with length, oops, 11, right? Consisting of year, age, race, and others, et al., etc., for some ith individual. So here we look at uh, each of these observations. These are observations. We look at them as individuals in the context of our wage data. So we can actually look at people as matrices in this case, in a mathematical context. What else? Other times, we will be interested in the columns, right? So other times, we are interested specifically in the columns. I spelled columns wrong. columns of X. And here we write it from X sub 1 to X sub B. And that vector has a length n, right? Here, I'm going to write it again in this notation. So here we say xj has vector length b, right? Oh, my bad, not b. I meant n. So here I say my xj starts at x sub 1j, x sub 2j, all the way to x sub nj. So here I'm saying that where j starts from 1 to all the way to b, right? So here now I'm interested in the columns, right? So I'm interested in this all the way to b. Or yeah, all the way to here. That's fine. Yeah. So sometimes we're interested in columns, sometimes we're interested in rows, depending on what we're looking for. But yeah, so for example, in our wage data, X sub 1 contains the n. So n again is the number of observations, right? Which is 3,000 values per year, right? And using this notation, the matrix X, okay, so we have certain notations that we can try. So using this notation, we're going to say matrix X can be written in the following format. We can say X is X sub 1, X sub 2, all the way to X sub B. Or we could also write it in this way. We could write it as X equals X transpose 1. So here we basically just transpose the thing. So if you guys looked at my my scientific computing course, I keep referring to that course because it's really, really the same as this one. Here we have a row, and if we transpose it, it becomes a column. And here I go XP, D. Oh, no, shoot, XP, XN. Now it's XN, right? Because if it's a column vector, which looks like this. Well, here we're looking at each row. Then here we're looking at it in a column way, in this way. So it can be written in these two things, but they mean the same thing, right? If we transpose this, we're looking at the columns. And if we transpose it again, well, we're looking at the rows. So here, okay, I just said it, but let me just write it out. The T notation denotes the transpose of matrix or vector, right? Okay, so we have, for example, let me write it in a different. So for example, let's go back to my matrix X. So here we can switch the roles of my columns and my vectors, my columns and my rows, right? So my n, if I transpose this matrix, right? So I transpose this matrix. Now my rows are switched. Why? What's gonna happen? Well, now it's reversed. My rows become my columns, and my columns become rows, right? I go, what's this? X to P all the way to X and P. I got like this, right? So now this is actually, just to make the notation nice, it's now an N by P. Originally it was, oh, it's also N by P. Oh, I just wrote it here, yeah. It's N by P. Where I go here, I have N rows, I have P columns. Here I have, oh, oh, I transposed it, but then my N and P are still the same. Yeah. Okay, yeah. I was just confused with the notation, but now my N becomes my number of columns and my P becomes my number of rows. That's what happens when I transpose a matrix, right? So that's a transpose of a matrix, while when I transpose a vector, well, now I have x sub I1, x sub I2, x sub IP, right? So what was this like initially before I transposed it? It was like this. Like this. Yeah. When I transpose this thing, now I get this one. I feel like I messed something up. Oh no, I meant when I got transpose of this. So here, basically, I'm just getting one of these, and I'm making this xi, where I, uh, where I goes from 1 to all the way to n. And then that's what I'm looking at here. But there's an xi transpose, that thing. So basically, the idea without getting bogged down by the notation is if we transpose a vector, let's say it's a column vector, that becomes a row vector. And if we transpose a row vector, that becomes a column vector. If we transpose a matrix, the row and the row and the column switch places, switch rows, right? Okay, what else can we say before I get bogged down by the notation as well? Uh, okay, let me look at this real quick. Now we use we'll use a vector. We use y sub I to denote the ith observation of the variable on which we wish to make predictions, such as wage. Okay. So here I'm just gonna write that. I'm gonna write that out. So we use y sub I, which is the ith observation um, of the variable on which we wish to make predictions. Or we make predictions. Such as finding the wage of a person. And so from here we write set of all and set of all uh, n observations in vector form. And we write it in this way. So we have y sub I, y1, y2, all the way to yn. So these are my observations, right? Because my n is my number of observations. And my p is my number of variables. Okay, thus our observed data consists of x1, y1, x2, y2, all the way to xn, yn, where each xi is a vector of length p. So we're going to say, why is this? Okay, I have to put this in the middle. We're going to say that our observed data is now the set of, it's a set of points. X1, Y1, oops, X1, Y1, X2, Y2, all the way to N. So it's a set of points or data, set of data points, where each X value is a vector of length P. And here, if P is 1, then Xi is simply a scalar. Scalar meaning it's a number. It's not a vector. That's what it means. So here we say, where do I put? If P is equal to 1, Xi is a scalar. Okay, in math, this makes sense, but I haven't seen how this can be applied specifically in the context of statistical learning. Okay, but in this text, the vector of length n will always be denoted in lowercase bold. Yeah, we're gonna look at that in depth. However, vectors that are not of length n, such as feature vectors of length p, as in 1.1, which is a vector. Okay, yeah, will be denoted in lowercase normal font. Scalars will also be denoted in lowercase normal font a in rare cases in which these two uses for in which these two uses for the lowercase normal font lead to ambiguity. We will clarify. Okay, just some notation. Matrices will be denoted using bold capitals. So I'm just gonna write that out. It's basically a capital letter. Then I would immediately know it's a matrix. Random variables will be a capital normal font. I'm gonna denote that along the way. I'm gonna tell you guys if it's a matrix or something else. Occasionally, we will want to indicate the dimension of a particular object. To indicate that an object is a scalar, we will use some notation, which is a real number, if it's a vector of length k. Oh, so here's one thing. Just some notation. If, let's say, some variable a is a number, then we basically use this notation to indicate a is a real number. Now, if a is a vector, so again, these are just unlocking notations. Then we use this notation. So that vector has row a by 1 dimensions. Or n, it doesn't matter. Could be that, or and if it's length n. Here it's length k, but it doesn't matter. Indicate that an object is an R by S matrix. So here we say A if capital, right? So if it's a capital, in this book, we'll use a capital letter for a matrix. So here we say something like A is an element of all real numbers, R by S. So this is an R by S matrix. That's what it says here. So we have avoided using matrix algebra whenever possible. However, in a few instances, it becomes too cumbersome to avoid it entirely. Okay, so they are trying their best to avoid matrix algebra or linear algebra, but at some point we're going to have to use it. And in these rare instances, it is important to understand the concept of multiplying two matrices. So here we're multiplying two matrices. So let's say, so suppose we have A and B, which are matrices, and we're going to characterize this matrices. These have R by D dimensions. B is a matrix that has D by S dimensions. So here, this shouldn't be too hard. You guys can look at my scientific computing video on vectors and matrices, because that's really all I talked about. I talked about all of these in depth and how this makes sense, right? I'm not gonna dive deep into it now because I'm also trying to study this thing. So here we have that. Uh, the product AB is computed by multiplying each element of I through A by the corresponding jth column of B. So so here we're basically doing a matrix by matrix multiplication, which I did talk about. And here this would have dimensions R by S, right? I'm not gonna talk about it now. So the product of that is, let's say, AB, and you have indices IJ, and we're going to equate them to, here we talk about a summation. This goes from D all the way to D. All right. Okay, let me see what K starts at 1. Okay. Now we have AIK. So here I'm multiplying every column of A to every row of B. Actually, this might be wrong. Wait. That's interesting. I think the notation is wrong. Because here oh no, here I'm multiplying the row. So that's why I'm moving at each row for my K here at A. And then here I'm moving at each so for A I'm moving like this. So this is AI1, AI2, AI3. Where K is 1, 2, 3 all the way to D. Right? All the way to D. And then here for B I'm doing the same thing. So yeah. We do an example here. I'm gonna skip that. Yeah, I'm gonna skip that. And it's only possible to do this multiplication matrix if the number of columns of A is the same as the number of columns of B. That's why these are the same. The number of columns of A are the same as the number of columns of B. I'm gonna skip that part. Okay. Okay, let me share this part now. I'm gonna go back to the book. There's the example if you guys want to try it out. Okay. So organization of this book, okay, so chapter 2, we're gonna talk about that soon, not now. It introduces the basic terminology and concepts behind stat learning, presents K nearest neighbor classifier. Chapters 3 and 4 cover classical linear methods for regression and classification. Chapter 3 reviews linear regression. Chapter 4 discusses two important classification methods, which are logistic regression and linear discriminant analysis. Yeah, so here now we're going into the statistical techniques used for machine learning. Or in statistical learning. So a central problem is choosing the best method given a problem, right? So at the end of the day, even if we use all of these techniques, these regression, these classification, these stuff, what's the best one to solve a given problem? And so in chapter 5, we introduce cross-validation and bootstrap, which can be used to estimate the accuracy of a number of different methods. So here now we're gonna test the accuracy of different methods. And much of recent research in stat learning has concentrated on nonlinear methods. However, linear methods often have advantages over their nonlinear competitors in terms of interpretability and sometimes also accuracy. Yeah, so here we have nonlinear and linear methods. Sometimes linear methods are better than nonlinear methods. Depends again on the problem that we're tackling. And in chapter 6, we consider linear methods for classical and modern. Okay, we have some stuff here: stepwise selection, ridge regression, uh, those stuff. Principal components, regression, lasso. I'm gonna talk about them as I'm going through the chapter. And then we move into nonlinear methods. So starting in chapter 7. Additive models. Chapter 8 is tree-based methods, bagging, boosting, random forests, support vector machines. Chapter 9 is deep learning. Chapter 10, no, linear and nonlinear classification is in chapter 9. Deep learning is in chapter 10. Survival analysis is chapter 11. Chapter 12 is unsupervised learning. Principal components analysis, k-means clustering, hierarchical clustering. And chapter 13 is a very important topic of multiple hypothesis testing. And at the end of each chapter, there's a Python lab section. So we're definitely going to go through that. And yeah, we're going to be introduced to Python. And yeah, the packages will be updated as there are new versions of Python. So right now, I think it was 3 point. I think it was something. I have to check actually. Let me check. What's the version of my Python right now? Let me double check. I think it was. Yeah, 3.13. I'm not sure if there's a newer one. Anyway, and there's an intro. Okay, so these are the different data sets to be performed in the labs and exercises in this textbook, and they're available in the ISLB package. What's this? Oh, may no longer correspond precisely to the results obtained by the reader. Oh, because the data updates. Okay, and we use this card. What's that symbol? To denote sections or exercises that contain more challenging concepts. These can be easily skipped by readers who do not wish to delve as deeply or lack the mathematical background. We'll try to do them. If we can't, cool. Data sets. So we illustrate stat learning methods using applications from marketing, finance, biology, etc. The ISLP package contains a number of data sets. It's only the US arrest data that's given in R, but they'll show how to access it in Python. Okay, they're also in a website, stuff like that. There's a website for this book, which you guys can check out. It contains a number of resources, including Python package associated with this book and some additional datasets. Yeah, and acknowledgements, and there we go, chapter 2. So I hope you guys enjoyed this video. Here we just did not really a brief introduction. We introduced some notation in math, which is cool. And yeah, I hope you guys are excited to go on this journey with me, and I'll see you in the next one.